Now we discuss representation of a function. How to represent a function or how to denote a function. We know a function is a relation from a set to another set. Suppose it is a function from the set A to the set B. And suppose xy, this whatever xy element of this f. That is, x is related to y or y is equal to fx. That is, this y is equal to fx. And y equal to this fx means this y is the image of x under f and x is the preimage. And this y, that is fx, is called the value of the function. Value of the function. Y is the image, of course, and that image is known as the value of the function corresponding to x. And now, if all these fx's, all these values are real numbers, then the function f is said to be a real valued function. A real valued function. Real valued function. That means the images in this B are real numbers. And therefore this B can be a subset of the set of all real numbers. In addition, if this A also consists of the real numbers, all elements in A are also real numbers. That is, A is a subset of the set of all real numbers. Then the function is said to be a real function. For real valued function, the values need to be real numbers. Images need to be real numbers. A need not be consisting of real numbers. But for a real function, A also consists of real numbers, that is subset of real numbers, or the whole real numbers. And also, when we say a function or when we discuss a function, we need always specify the sets A and B, the domain and the codomain. But in almost all our discussions, these sets A and B usually will be the subsets of the number systems, either subset of integers or subset of rational numbers or subset of real numbers. And if nothing mentioned about the domain and codomain, only say this is a function simply, then it is understood that it is a function from the set of all real numbers into itself, f from R into R. In this situation, this domain and codomain will not be or need not be specifically stated. That means in this situation, this f is a real function. And now, come to the representation of a function. We know this f consists of all such ordered pairs, x element of R, y element of R, and y is equal to fx. And now This R consists of infinitely many elements. So representing this R by a roster method is practically impossible because there are infinitely many ordered weights. So writing all these infinitely many ordered weights is practically impossible. The arrow marking representation is also impossible because there are infinitely many arrows from this R into R. Practically impossible. So the only method that can be adopted is the set builder method. We build the set. We build the set. The method is this, that we know, that we have discussed in the case of relations. The method is this: F is equal to set of all such ordered weights x, y with x element of R, y element of R, and specify the rule connecting this x and y. If there is a rule with which we can represent. Otherwise it is impossible. In the case of this infinitely many elements, if there is a specific rule with which we can find these x and y, or this y, we know as x set of all elements in R. And if we can find y by a specific rule, then we state that specific rule here. So this x, y, x comma y element of R, and that rule is y equal to x. And if the function is from R into R, we need not specify the sets. We simply say f is a function. And in this situation, we need not write always this form to represent this complete form of this representation, this set builder form. We need only write the rule with which we can find this y. That is, this y is equal to fx. Simply we write this. Simply we write this. Therefore, if we are given y is a function y equal to fx, only say y equal to fx, then it is understood that f is a function from R into R. F consists of such ordered weights xy element of R, and y equal to fx. This specific rule is only mentioned here. For example, suppose we are given a function, say fx equal to x squared. Fx equal to x squared. Only given function fx equal to x squared. Then from this, it is understood that this f is from R into R, and f consists of such ordered weights x, y with the xy element of R, and y is equal to x squared. Y equal to x squared, or fx equal to x squared. That is, this consists of all elements of the form x squared, x element of R. So this is the function x squared. This is the function. So this is the representation. The shortest form of the representation of a function is this. Only specifying the rule with which an x in R is related to this y in R. That rule is this. If f is given to be the function, say by fx equal to x squared plus 1, then this f is a function from R into R. consisting of all ordered weights of the form x squared plus 1 with the x element of r. X element of r. This x squared plus 1 is y fx. So x squared plus 1. Such ordered weights, the totality of all such ordered weights constitute this function. So this is the shortest form of representing a function. Always we will be given a function in this form by specifying the rule with which an x is related to this y. This y is actually this fx, x squared plus 1. So that's all.